Hello there. Thanks for joining me as we go into our final lesson in our periodicity topic. Today's lesson, we are looking at the periodicity of period 3 chlorides and other elements. For our lesson objective, we're going to understand the periodicity of the period 3 chlorides and for other elements in the periodic table. Learning outcomes we'll be addressing just below there. So we've been looking at this concept of periodicity, which to remind is just the fact that there are certain patterns that you see across the periodic table. These are both in the physical properties and the chemical properties of the elements and their subsequent compounds. We define it as the repeating patterns and properties of the elements as you move across the periods of the periodic table. We looked last lesson, at the first lesson at the physical properties, and then last lesson we looked at the chemical properties of the oxides. This lesson is focusing on the periodicity of the period 3 chlorides. So to begin with, let's have a look at the chlorides that they would make. Sodium chloride through to sulfur dichloride. First thing I want you to do is to have a pause and work out the oxidation number for each of these elements in the period 3 that we see for the chlorides. And can you tell me what the trend is? Pause now and check the answer now. We know that our chloride is always going to be -1 unless it is bonded to a fluorine, which is the more electronegative atom than the chloride. So based on that, we got a bunch of neutral compounds. Group 1s are always +1. Group 2s are always +2. So +1, +2 for sodium and magnesium accordingly. We have 6- because we have 6 single minus chlorides, and then we got 2 Als, so that's going to be the +3 oxidation state, +4, you can see a bit of a trend arising, +5, because we got 5-, that's going to be +5. Then we get to the sulfur, where it's going to be, that's going to be -2, we go down to +2. We had a pretty clear trend going up to the phosphorus, but then we have a very small number for the oxidation number of the chloride of sulfur. Let's have a little deconstruct of why that is. So we saw all positive. We see a rise in the oxidation number as we move across the period. That's the periodicity. That's because chlorine is the more electronegative than all of these atoms. We see a rise until sulfur. Let's have a think about why that is. From sodium through to phosphorus, they are all using their valence electrons in the bonding to chlorine. We'll see that sulfur is not using all its valence electrons, so therefore it's not going to have that +6 oxidation state that we might expect. Let's consider the sodium and magnesium. We know sodium is going to have 1 valence electron, group 1. Magnesium is going to have 2. These are both ionic compounds, so sodium is going to lose the 1, magnesium is going to lose the 2 to be +1 and +2 respectively. The aluminium chloride is a bit of an interesting one. We'll just skip over that for the brief moment, and we'll look at these simple molecular ones on the right-hand side. Silicon chloride. Silicon group 4 has its 4 valence electrons, so we're going to have a sort of tetrahedral arrangement when we bond with the chlorines. We're using all 4 electrons in the valence. Chlorine is the more electronegative, it's going to be +4. Phosphorus pentachloride, group 5, we've got all 5 of the valence electrons. This is a case of expanding the octet, and we'll end up with a sort of trigonal bipyramidal geometry, something along the lines of that. But what's important for us now is we can see it's using all 5 of its valence electrons. The chlorine is going to be the more electronegative atom, so it's going to be a +5 oxidation state. The sulfur dichloride, if we go over here, sulfur in group 6, we got 1, 2, 3, 4, 5, 6. Let's think about this. We're forming a bond with 2 of the chlorines. So we're going to have 2 chlorines bonded, and then we're going to have 2 lone pairs of electrons to give that V-shaped molecular geometry. As we can see, only 2 of the sulfur's 6 valence electrons are being used in the bonding. The chlorine is going to be the more electronegative, so it's got the +2 oxidation state there. Let's consider this aluminium chloride. Al2Cl6 can be thought of a covalent dimer of AlCl3. So you might have seen that and go, why can't you simplify that just to AlCl3? Because AlCl3 we can think of as being very much a ionic compound, Al3+, 3Cl-. But what we observe is that without water, we actually get a covalently bonded molecule, which can be thought of as a dimer of AlCl3, where we're forming coordinate bonds from the chlorine. So a dimer is where you've got a monomer, which mono meaning 1 unit, and a dimer, di meaning 2, you've got a 2-unit compound that forms from 1 unit. So we can think of the Al2Cl6 as a dimer of an AlCl3. Let's draw that so we can better understand what we mean by that. What we have is we've essentially got a covalently bonded compound where we have our aluminium bonded to 3 chlorines. Because of the 3 valence electrons, we know it can do that. However, the aluminium has a vacant orbital there, and the chlorine has a lone pair of electrons. Well, it's got a few lone pairs of electrons. So what we can observe is that the lone pair can form a dative coordinate bond with the empty orbital of the aluminium atom, and we can get this dimer situation where we have essentially the second AlCl3 forming like that, and then this one can form a dative bond with one of its lone pairs of electrons to the aluminium chloride's empty orbital of the other unit. And we get this sort of structure here, where we've got 3 covalent bonds, a dative bond, and in the second part of the dimer, 3 covalent bonds and the dative bond. Because when we say ionic and covalent bond, we're talking really about 2 extremes of a spectrum, where a completely covalent bond is at one end of the spectrum and a completely ionic bond is sort of the other extreme of the spectrum. And really there's a whole range of bond polarity that can exist between these. But we don't need to worry about that right now. It's just something I thought is worth mentioning. So that's what we get. We get this covalently bonded dimer with the coordinate bonds between the chlorines and the aluminium atoms. Then we saw our silicon chloride, phosphorus pentachloride, and sulfur dichloride are all covalent. Note the non-bonding electron pairs on sulfur, thus the change in the trend of the oxidation number. That is what we saw just before. What we're interested in looking at now is some of the chemical properties and seeing the periodicity that's observed in the chemical properties of these period 3 chlorides. So we've seen that trend in the oxidation numbers. Let's look at the chemical properties. As with chemical properties that we saw with the oxides, we need to consider the bonding and the structure, because that's going to dictate how it's chemically going to behave with water. Let's have a look here. So we got 2 giant ionic, our sodium and our magnesium chloride. Giant ionic, cations, anions, straightforward lattice there. Then we had our simple molecular at this end, and we also said that Al2Cl6, rather than being a ionic compound, rather it's a molecular compound that can be thought of as a dimer. So we're going to branch them into 2 categories and see how they behave. Firstly, the giant ionic. Giant ionic chlorides of sodium and magnesium won't react with water. So we don't see a chemical reaction, rather we see a physical phase change where they dissolve and they move into the aqueous phase. Why don't you take this as an opportunity to see if you can write ionic equations to represent the dissolution of magnesium chloride and of sodium chloride. So we don't have a chemical reaction, we just have a phase change. Pause, see what you come up with, and then check it here. So when we're talking about a phase change, we've got a solid sodium chloride, and we're going to dissolve that into the separate ions. So all we have to do is just go from the ionic solid to the aqueous ions. Now there's a few ways you can represent this. You can simply write water over the arrow like that to show that it's dissolution. Or you can go plus AQ. Now you can do this because the water is in such a large proportion when compared to the salt that we can just say that we're putting it in the aqueous phase. Similarly, magnesium chloride, it's going to be the same thing, only we've got a different ratio of atoms, so we're going to have a different stoichiometry, but that wasn't too hard to figure out, I don't think. You're just going to need an Mg2+ in the aqueous phase with 2 chloride ions in the aqueous phase, like that. And that is what we observe here. Now, more interestingly, let's look at the simple molecular ones because we do see a chemical change when they are placed in water. Each of the simple molecular period 3 chlorides will react with water, emitting HCl gas. Al2CO6 is a bit different to the others. Let's look at this. This will break down. Al3 plus and Cl minus will enter the solution. The Al3 plus becomes hydrated to form an octahedral hexaaqua ion complex. This causes a water molecule to lose a H plus and therefore the solution will become acidic. So what's that? That was a big sentence there. We have this aluminium hexaaqua, meaning it's got hex 6, aqua meaning water, 6 waters bonded to it. It becomes a complex ion in this octahedral geometry. Now this isn't something we need to be able to do just at this moment, but we can consider this. Essentially what happens is the aluminium ion with its 3 plus charge forms dative covalent bonds with water molecules and we get a octahedral structure where each of these bonds are at 90 degrees to each other. And this is what's called a complex, and it's an ion, so it's a complex ion. So it forms this sort of species when dissolved with the 3 plus. It's called a complex ion, I suppose, because it's more complicated than a simple ion. But we don't need to know about that. All we need to know is that we become deprotonated, we lose a H plus, and that will turn the solution acidic. H plus, we now have a source of hydrogen, and that's what acid is. It's a hydrogen donator. So we can form a bond with a Cl minus and emit HCl gas here, hydrochloric acid. Our SiCl4, PCl5, these are a bit more straightforward. These react to release fumes of hydrochloric acid. Why don't you pause now, have a go, see if you can write an equation for both of these. So we're going to start with these. We're going to react with water, so plus H2O. See if you can work out what the product's going to be if we're forming HCl, and the product of the silicon is going to be this silicon dioxide. Give that a red hot try and we'll flick over to the board and write it together. So we had our SiCl4 reacting with water, and we have our PCl5 reacting with water as well. Let's put some states here. This is in a liquid state. This is in the solid state, H2O in the liquid. So we said that for this one, we form a silicon dioxide, which is a solid, and we have our HCl as the byproduct. So we have a chemical reaction that we emit the vapor of the hydrogen chloride gas. PCl5 plus H2O, bit similar. What we form is an aqueous phosphoric acid and our HCl gas as well. And they should all be nice and balanced. No, they are not. Let's have a look here. So we're going to want 4 of those, 2 of those. That should make the top one balanced. And then at the bottom, we're going to have, well, let's have a look, 5 of these. And then 4 of them. And that should be our answers there. Now, sulfur dichloride also reacts to form hydrochloric acid, but that's not an equation that we need to know just at this point. Excellent. So let's conclude this periodicity lesson by branching out a little bit beyond just our period 3 elements. Because we've been focusing on the period 3 elements for the duration of this course, but we've said that periodicity is the trends across the whole periodic table. So let's just illustrate some of these trends beyond just what we've been focusing on. Now the key word here is trends. So there can be some exceptions. We do see some things that go against our trends, but the general nature of it does follow this periodicity that we've been looking at. You can use our understanding of periodicity or to predict characteristic products of an element in a given group. You can also use the data given about the chemical physical properties to suggest the nature or the possible position on the periodic table. Let's look at 2 examples, the first ionization energy and the melting point. So if we look at this period by period, we got period 1, just our hydrogen and helium, period 2, period 3, 4, 5, 6, 7, etc. Now, obviously, as we go down the periodic table, we start to introduce some new types of elements. We get our D blocks and our transition elements. We get our lanthanides, our actinides, our F block in there. So we'll see some different trends for those. But what we can note here is that if we focus, let's say, on our P block, we can see we've got the general trend in the ionization energies on period 2. We see that same trend on period 3, same trend on period 4, period 5, period 6, so on and so forth. I mean, even the ones that we haven't looked at, if we look at the D block, our sort of transition element area, we've got a trend there. We can see that same trend in the next period down, similar trend in the next period down, so on and so forth. Same with our F block there and there. You can see these similar trends. And I just want to reiterate, they are trends. They're not, it's not set in stone. There are some exceptions due to the chemistry and the specific instance of each individual atom. We can have some variation in these trends, but the general properties does be observed like we see it. Here's another one. If we consider the melting point, you can see that we have the 4th period as the blue, 5th period as the green, 6th period as the red, and we can see this periodicity follows for the periodic table. Now, why is this so useful? Because like I said up here, if we can consider the periodicity trends and what we know about structure bonding or the chemical physical properties and the, where it is on the periodic table, then we can potentially identify or narrow down, areas that an unknown element could belong to just based on these properties that we have. Or if we know, if we're doing it the other way where we've got an element on the periodic table, we could be able to infer certain periodic certain physical or chemical properties that it has based on where it is in the table. Here's a question that you can have a go at to finish off. I got 3 elements that are all next to each other, and we're looking at the first ionization energy as we increase the atomic number by 1. Here's the question, pause and have a think. Which of the following could be the first element, that spot there in our above graph, out of magnesium, fluorine, carbon, or nitrogen? Have a think. And the answer is, it would be fluorine, because this is very characteristic of what we know for our trends in the first ionization energy. And we can see that this is that little bit that we see as we approach our noble gas, and then we have a huge drop as we go to the next quantum level. We can see it here as we go from fluorine to neon sodium. We see it here for chlorine, argon, potassium. We see the same trend there, all down the periodic table. So we know that it can't be any of the others because they don't follow what we know about the periodicity for the first ionization energy. It has to be fluorine because that would follow this trend. And with that, we finish our lesson and our unit on periodicity. What have we done? We've described the reactions, if any, of the elements. We looked at oxygen last time. This time we looked at chlorine. Stated and explained the variation in oxidation number of the chlorides. Described and explained the reactions of the chlorides with water. Interpret the variations and trends in terms of bonding and electronegativity. And we suggested the type of chemical bonding present in chlorides and oxides from observations of their chemical and physical properties. And then we predicted the characteristic properties of an element in a given group by using knowledge of chemical periodicity, and deduce the nature, possible position in the periodic table, and identify of unknown elements from given information about physical and chemical properties. Here are the tasks for this lesson. Pause now, work through them to consolidate your understandings. Well done. That is the end of our first unit into inorganic chemistry. See you on the next one when we start the next one. Have a fantastic day.